Alright, we're getting ready to start some more with the fundamental theorem of calculus, and we're also going to be talking about some other theorems used with integrals. This first problem, what we're going to do is we're going to find the area of region bounded by the graphs. And so what we're going to need to do is actually figure out what this looks like. This graph is actually 3 the square root of x minus x to the 3/2, or we could say it's 3x to the 1/2 minus x to the 3/2. I'm going to know if I plug in 0, I get 0. And the other value that's going to give me 0 is going to be 3. I don't really care what's going on in between there. I just know that it is going to cross the x-axis at 0 and 3, so I can go ahead and use those as my bounds. So I'm going from 0 to 3 of this 3x to the 1/2 minus x to the 3/2 dx. So what I'm going to do is integrate each one of these. So I have 3x to the 3/2 over 3/2 minus x to the 5/2 over 5/2. And I'll be going from 0 to 3. This ends up being 3 times 2/3, which would be 2x to the 3/2 minus 2/5 x to the 5/2. Well, what I'm really worried about is what I get when I plug in 3. And when I plug in 3, I end up getting 2, maybe 3 square root of 3. Or I could say it's the square root of 27, which is the same thing. Maybe I'll go ahead and write that way because that's probably how most of you are doing it. So it'd be the square root of 27 minus 2/5, and then when I plug in 3, I have 3 to the 5th power. 3 to the 5th power is 343, so I have the square root of 343. When I simplify all these things, I'd have 2 times 3 square root of 3 minus 2 times 9 square root of 3 all over 5 here. That would give me 30 that would give me, I need to come up here for I have more space, 6 square root of 3 minus 18 over 5, and I'd have a square root of 3. I could make a common denominator and make it 30 square root of 3 over 5 minus 18 square root of 3 over 5, and I'd get 12 square root of 3 over 5. Now it's a lot of work. You could have just made it into a decimal as well. Let me begin to talk about this and then use this in the next example. It is the mean value theorem for integrals. I'm going to try to draw a picture for you of what mean value theorem is really saying. And what it is saying is that you have some curve, and it's going from A to B. And it's saying the area underneath this curve can be equal to some value of C. Okay, so if I come up here, some value of C, maybe I'll do that in red. And I draw a line across and then down this other area, so I'm going to shade that in red. So the area in black would be equal to the area in red at some point for C. This C is the height of the rectangle, this F of C is the height of the rectangle, and then this is the base of the rectangle. So what it's saying is that the area under the curve is equal to some rectangle that we can create between those 2 points A and B. This example, which I'll start in the next video, is asking you to figure out what is that C value, which will make the integral and the area underneath the curve equal. In order to start this next problem, which I began on the last video, I'm going to go back to the theorem, kind of briefly remind everybody what I was doing, is that we were talking about the area underneath the curve, the area in black right here. And we want the area in the black to equal the area in red. So there's some value C that when you plug it into the function, that becomes its height, and the height times the base, that rectangle, the rectangle in red, is equal to the area underneath the curve. And so what we're going to do, and I've gone ahead and drawn this curve, is we have 9 over x cubed. And what we're doing is we're going to look and find this area underneath the curve. And what I want to know is, when does that area underneath the curve equal, what is that area first of all, and then when, or what value of C, okay, so maybe it's right here, okay, what value of C, if I was to draw a rectangle in, would I get the same equal area as the area underneath the blue? So the first step is to actually find the integral, or find the area underneath this curve. So I will do so by integration. I get 9x to the negative second over negative 2 from 1 to 3. And I don't want to plug in numbers in this way, so I'm going to say it's negative 9/2 x squared from 1 to 3. That gives me a negative 9 over 3 squared is 9 times 2 is 18, minus, we're going to plug in 1, and I get negative 9/2. What that does is it gives me the answer of negative 1/2 plus 9/2, which is 4. So I want to know what value of C, okay, if I call this the C, what height, so we're going to plug in that C value into our function, will give me the same area, the area in blue. So I also need, this is the height, and I need times the base. So the base is the 3 minus 1, so it has a base length of 2. Well, I'm going to be able to go ahead and solve for this, so I'm really looking at f of c times 2, and actually let's go ahead and just divide by 2 on both sides, so I have f of c by itself. So we want to know, when is the height of this function 2? So the function itself is 9, and I'll go ahead and replace the x with a c because that's what I'm talking about, 9 over c cubed. I can then cross multiply and get 2c cubed equals 9, and then divide by 2, and I get 9/2. So my c value is the cube root of 9/2. Now if we want to know what number that is exactly, we'd have to use our calculator to compute that. So I'll do 9 divided by 2, and then I'll take the square root of that, or the cube root of that if I can on here. Looking for the button, I'm not finding it. So I'm not sure if I can do it on this one or not. So let me see if I can compute that really fast with the calculator I have laying here. Y'all just have to take my word for it, and you guys can plug it into your calculator. So we're going to take that to the 1/3 power. That gives me 1.5. Oh wait, I couldn't have put that in there right. Sorry about this. To the 1/3. That gives me 1.65. So this is approximately 1.65. So it does look to be about right here in my picture, maybe a little bit further left. But if I was to find the area of this rectangle, okay, it would equal the area underneath the curve. That's what mean value theorem for integrals says. All right, this next part that I want to get ready to talk about is called the average value of a function. And what it talks about is really, what is its average height? So I want to give you an example. If I draw a picture real quick that looks like maybe from here to here, we could say that its average height might be right about here. Okay, so we're talking about, when we're finding the average value of a function, we're talking about what is its average height. I want you to keep that in mind. This is a formula that you definitely have to know. You know to use it when it says find the average value of a function. So that's exactly what we're going to do. We're going to find the average value of the function. We're going to use that formula. So it's 1 over b minus a from a to b of f of x dx. So my b and a value are right here. So I'm going to do 1 over 3 minus 1 from 1 to 3 of my function right here. Let's go ahead and simplify this. This would be just plain old 4. 4x squared divided by x squared would be 4. Plus 1, well, I'd have to distribute my 4 through. So I'd have 4 x to the negative second. And we will go ahead and integrate this now. So we'll have 1/2. I'd have 4x, wait, I didn't mean to write the integral in front of it because I am integrating. So let's say 4x plus 4x to the negative 1 over negative 1 from 1 to 3. So that's going to give me the answer of 4x minus 4 over x from 1 to 3. So I'll bring that up here and I'll have 1/2. Plug in my 3, I have 12 minus 4/3. Remember, I'm multiplying the whole thing times 1/2 at the end. So minus, plug in your 1, 4 minus 4 again. So this ends up giving me, well, that'd be 36 over 3. 36 minus 4 is 32 over 3 minus 0. So I end up getting 32 over 6, which will reduce to be 16 over 3. So what it's saying is that my average height is 16/3. My last example is asking me to find the average rate of flow. So this is asking me to use average value theorem. So 1 minus b minus a f of x dx. A happened to be 0 and r, so I'm going to be doing r minus 0. From 0 to r, function k big R squared minus little r squared dr. Now I'm taking this with respect to little r here. So is k over r minus 0 is r. And I'd integrate big R squared minus little r squared dr. We'll come up here and finish this. So when I integrate, I get big R squared little r minus little r cubed over 3 from 0 to r. So I have k big R over big R. Plug in big R, I get big R cubed minus big R cubed over 3. And then I would just be subtracting off 0 here. So what I end up, my answer getting would be 2 big R cubed over 3, which would simplify into 2 big R squared k all over 3.